For this lecture, we'll cover the chi-squared tests for goodness of fit and independence. These tests are designed for qualitative or categorical data, where the observations can be counted but have no inherent measurement. In this way, they are more similar to proportions tests than they are to means tests. Let's start with the goodness of fit test. Say you wish to test that babies are born more or less often on certain days of the week. Being born on a Saturday has no measurement associated with it, but it is distinct from being born on a Tuesday, making this a categorical variable from birth to birth, with 7 possible outcomes, those being Monday through Sunday. Or, what if you wish to test that the proportions of various colors of M&Ms differ from the advertised proportions? Red is definitely distinct from brown, which is distinct from yellow or blue, but again, there is no measurement associated with these colors. It would be impossible to calculate an average color, for instance. These tests are definitely proportions tests, but now there are more than 2 outcomes possible. It's not just success and failure anymore as it was with the past proportions tests, so we need a new proportions test, a proportions test that can account for multiple outcomes. Let's take that first example. Are babies born with different proportions on certain days? Test at the 5% level of significance. Here's what your hypotheses look like. Remember, we were testing to see if there were different proportions among the various days. The null hypothesis is thus that all proportions are equal. And in this case, that would mean that each day has a 1/7 probability or 1/7 proportion of occurrence. Here we gather the data. We gathered 700 random births that were selected from local hospitals and counted up the births by day of the week. There were 110 on Monday, 124 on Tuesday, so on and so forth until there were just 84 on Sunday. The total here again would add up to 700. That's our sample size. In our critical valued approach, the critical value will come from a chi-square distribution with degrees of freedom equal to the number of outcomes minus 1. There are 7 possible outcomes for each birth, and 7 minus 1 is 6, so 6 degrees of freedom. If you go to your chi-squared table to the 5% column, the 6th row for 6 degrees of freedom, you'll find 12.592, and that is our critical value. To calculate the test statistic, we first need to create a hypothetical data set of what the null hypothesis expects from 700 births. Recall that the null hypothesis expected a 1/7 proportion for every day. Since there was a sample size of 700, 1/7 of 700 means we should expect 100 births per day if the null hypothesis were true. So we're creating a table of what the null hypothesis expects so we can compare the actual data to the null hypothesis expectation. The test statistic is probably a little more complicated than some of our other test statistics, but it can still be done by hand and definitely by calculator or on Microsoft Excel. To calculate the test statistic, we subtract each day's expected births from each day's actual births. Then we square each one of those differences and divide by the expected number of births. Once we're done, we add them all up, and that's our test statistic. You can see it done in the chart below. There were 110 births on Monday. The null hypothesis expected 100 if all proportions were to be equal. So if we take the actual minus the expected, we get 110 minus 100. That's 10. We square it to get 100, and then we divide by the expected number, 100, and 100 over 100 is 1. If we use 124 and 100, we subtract them to get 24, square them to get 576, divide by the expected 100 to get 5.76. Try it for the rest of these to make sure you get the same numbers I do. Now, if you add each one of these up, you'll get 19.12, and that is our test statistic. Moving on to the decision and the interpretation, we see that the test statistic of 19.12 is more extreme than the critical value of 12.592. This leads us to a rejection of the null hypothesis because the test statistic is extreme, showing evidence against the null hypothesis. We would conclude that there is sufficient evidence at the 5% level of significance to suggest that the proportion of births on each day differs from 1/7. Now here it may be interesting to know which days are most different. If you go back to the test statistic calculations, you'll see the highest two test statistic contributions came from Saturday and Tuesday. Saturday we saw an especially low number of births, and Tuesday we saw an especially high number of births. So if we reject the null hypothesis, it's worth going back and looking for the categories which were most extreme. So I might say specifically we saw the most extreme observations on Tuesdays and Saturdays, where the data suggests that fewer births occur on Saturdays and more on Tuesdays. To do this test on your TA84 calculators, you need to go into Stat Edit, first option, to edit your lists. Recall that to edit a list, you go to the list header. I have it selected here. I press Clear and Enter. Now the list is gone. I'm also going to need list 3, so I'm going to Clear and Enter. Your lists may be L1 and L2 or L4 and L5. Not a big deal. Just remember that I'm using L2 and L3. First, I enter the actual data, the actual births in this case, into a column or into a list. So that's 110, 124, 104, 94, 112, 72, and 84. Those would be my actual observations, my observed values. Now I come over to list 3, and I'm going to enter all my expected values, which is easy because it's all 100 in this case. Now that I have both lists stored, the list of observed or actual values and the list of expected or null hypothesis values, I come back into Stat, I go to Tests, and I go to my chi-squared goodness of fit test, chi-squared GOF test. Now my observed or actual observations occurred in list 2, and my expected were put into list 3. I should have 6 degrees of freedom, and now I can calculate. Notice the test statistic of 19.12 is exactly what we got before. The calculator can give us a p-value here. So the calculator tells us that the probability that we would get something this extreme, given the null hypothesis were true, is only about 0.4% or 4 1,000ths. That probability should lead us to reject the null hypothesis because it is an implausible hypothesis. Again, the typical rule is that if the p-value is less than 5%, we reject the null hypothesis. If you look down a little bit further, you can scroll to the right and find each one of the test statistics we calculated by hand before. It's not the most convenient presentation, but at the very least you can get the p-value quite easily. Our next chi-squared test is the independence test. Sometimes I call it categorical correlation. We've done linear correlation before, where we test for relationships between quantitative variables. Those would be variables like height and weight, or SAT math score and high school GPA. These are inherently quantitative. We can ascribe numbers to them. Linear correlation and regression assess relationships between these types of quantitative variables. But what if we want to test for a relationship between, say, your political affiliation and your affinity for certain alcoholic drinks? Being Republican is not measurable in and of itself, nor is preferring tequila shots. The independence test is used to see if proportions of one variable tend to change whenever a second variable changes. For example, are Republicans more likely to prefer tequila shots than Democrats? Are beer drinkers more likely to be political independents than wine drinkers are? In a test like this, the researcher's hypothesis is that there is a correlation between the two categorical variables. Let's stick with our example of political party affiliation and alcohol preference. Is there evidence at the 5% level of significance to claim that political party affiliation and alcoholic drink preference are correlated? Here, our null hypothesis is that the two variables are completely independent of one another, that your political affiliation has nothing to do with the alcohol preferences you have. The researcher's hypothesis in this case is that the political party affiliation does correlate to drink preference. In general, the alternative hypothesis will be there is a correlation between variable 1 and variable 2, depending on what your two variables are. In step 2, we gather the data. 225 registered voters were polled about their political party affiliation and their preference for various alcoholic beverage options. The chart is shown below. If you remember from probability class, this is called a contingency table. It's a table that crosses one categorical variable with another. Of the 225 total, 45 were both Democrat and liked beer. 4 were both independent and liked tequila shots. If you add up all of these, you'll get 225. I've also shown the totals of each column and the totals of each row here because we'll need them later. In our critical valued approach, we again look to the chi-squared distribution for a critical value. But this time, the degrees of freedom will be equal to the number of rows minus 1 times the number of columns minus 1. You might write it mathematically as r minus 1 times c minus 1. There are 3 possible outcomes for party affiliation, those are our rows, and 4 possible outcomes for alcohol preference, those were our columns. So 3 minus 1 times 4 minus 1 gives us 3 times 2, which is 6. And we have 6 degrees of freedom again. Again, the critical value comes from the 6th row of our chi-squared tables at the 5% level of significance, which gives us the same 12.592 that we've seen before. To calculate the test statistic, we first need to create a hypothetical data set of what the null hypothesis would expect from independent variables. This is similar to the last chi-squared test, but the methods are a little bit different. We need to find an expectation for each cell of our data table. Remember, there are 3 categories of political affiliation and 4 categories of alcohol preference. That means we're going to need to fill 12 of these. That's going to get a little bit tedious by hand, so I'm going to show you how to do it on the calculator, and I'm going to leave a Microsoft Excel document available to you. The formula here for the Democrat beer cell would be taking the beer column sum times the Democrat row sum divided by the total sample size. Let's go back up to the data and take a look at what those numbers would be. The beer column had a total of 95. The Democrat column had a total of 100. We would multiply those two things and divide by 225. You should get 42.222. Check at least a few of these by hand to make sure you understand the process. Now, to calculate the test statistic, we do almost exactly what we did in the goodness of fit test. For each cell of data, we calculate the actual count minus the expected count, we square it, and then we divide by the expected amount. So again, the formula, actual minus expected, squared, divided by expected. For the Democratic beer cell, we get 0.183. Again, check a couple of these to make sure you're getting the same numbers to the nearest thousandth. The test statistic will again be the sum of all the values in this third chart, and in this case, you should get 1.149. That brings us to our decision and interpretation. We cannot reject the null hypothesis in this case, since the test statistic of 1.149 is not more extreme than the critical value of 12.592. In this case, there is insufficient evidence at the 5% level of significance to suggest that political party affiliation correlates to alcohol preference. This is probably something we should have expected, as it doesn't make any sense for a certain political party to enjoy a certain type of alcohol any more often than another certain type of alcohol. You'll be happy to know that we can do this one on the calculator. We're going to need to enter our information not as lists this time, but as matrices. A matrix is basically a code language in mathematics for a chart. First, we want to make sure that our A and B matrices are clear and ready to go. So let's go into second memory, scroll down to memory management and deletion, scroll down to matrix, and you'll notice that I have a matrix stored in matrix A. I'd like to get rid of that. So I press the delete button and it's gone. Now I can use matrix A for this test. I go to second matrix, I go over to edit, and I'm going to edit matrix A, so I press enter. Matrix A has 3 rows and 4 columns, so it is a 3 by 4 matrix. Now I'm just going to enter the data that I see over here that I collected earlier. So 45, 30, 15, 10, 40, 32, 16, 12, 10, 7, 4, and 4. Now all my data is stored in matrix A. I don't have to save it or anything. Now I can come into stat, tests, and I can use my other chi-squared test. It's the one that just says chi-squared test. In this case, my observed matrix, the matrix of data values, is A. I want my expected matrix to be B. So I'm going to delete this one. I'm going to go second matrix, and I'm just going to scroll down and choose B. Now the calculator will calculate my expected matrix, and it will store it into B. It will also calculate my third matrix and give me the test statistic and the p-value. There's the test statistic we got before of about 1.149. Our p-value in this case is so high that we are forced to accept the null hypothesis, as we saw with the critical valued approach, and it reminds us that our degrees of freedom were indeed 6.